last time we finished the proof of Sharpe completeness of this special problem of computing permanents on 0-1 matrices, right. So, let us write down that theorem which we proved. So, this theorem is due to Valient, it is quite old. So, we showed that permanent on 0-1 matrices is Sharpe complete. Okay, that is what we showed. So, Sharpe completeness means that if you can solve permanent, then there is an efficient Turing machine, deterministic polytime. It can actually compute any problem in Sharpe in that much time. And so, that makes permanent very different from determinant, because in a way this means that there is no hope of computing permanent in real life, in practice, because Sharpe complete means that in particular it is harder than sharp SAT, as hard as sharp SAT. So, it is harder than SAT, right. So, it is harder than NP hard. So, what we will do next is we will compare these two new things, pH and Sharpe, right. These are really new complexity classes. So, let us compare these two and how they fit in P space. Both of them are P space, are in P. So, pH and Sharpe are both natural generalizations of NP. pH uses alternations. And the second one, Sharpe, this uses counting. So, either quantifier alternations, they exist for all alternating on strings, right, and only constant many for pH. If you make it unbounded, then you will get P space, which is where pH is. And Sharpe uses counting. Okay, so instead of there exist, it asks how many strings exist. It's a counting question, and that also you can do in P space. So, the interesting question is, how do they compare? Are they unrelated, or is one contained in the other? Then which one? So, in the 80s it was thought that they are incomparable. They were thought to be incomparable because pH has NP and NPs can be solved using Sharpe, but then NP to the NP looks like something very different because it has for all quantifier, right. So, we do not know how to convert, it is not very clear whether for all can be reduced to counting as well, and then there exists for all, whether that can be reduced to counting. So, they were thought to be incomparable. So, it was surprising when they were shown to be tightly related. So, eventually Toda proved in 1989 that pH is actually contained in p to the sharp p, and hence also PP oracle. So, if you are given a PP oracle or a sharp P oracle, then you can solve anything in polynomial hierarchy, not just NP but also NP to the NP and so on. And this is a highly interesting proof because it will use randomization. Notice that this is a containment of deterministic classes, but this will be shown amazingly using randomization, probabilistic methods. So, proof unexpectedly uses randomization. Okay, it's not clear why it should use randomization because there is no random bits in the question, but that's what we will do. So, this will be a very long proof. So, let's begin. The basic ideas will be very interesting and novel for you. So, Toda 1991, that pH is in p to the sharp sat. In other words, if you can solve sharp sat, then you can solve NP to the NP, sigma 3 and so on. So, what is the overall idea? So, overall idea is we will give a reduction, basically reduce sigma I sat to a new problem that we will call parity sat. Okay, so this will be stronger than, I mean, this is we will not just reduce it to sharp sat, but actually something weaker than sharp sat, which is parity sat. Parity sat, as the name suggests, is the question of checking whether the number of satisfying assignments is odd. Okay, if it is odd, which in particular also means that there is some assignment, because odd number starts with 1, 1, 3, 5, so on. And if there is no satisfying assignment, then that is 0, so that goes in, that's a no instance of parity sat, but it is also possible that number of satisfying assignments is 2 or 4 or 6, they also are no instances. So, let us define this problem and a new complexity class. Let us do that. So, we will do this by randomization using hashing. Okay, so we will actually reduce sigma I sat to parity sat by hashing. Hash functions, that is the place where randomization will help. So, let us define few things. So, parity sat is the problem of identifying whether a given Boolean formula phi is a Boolean formula with number of satisfying assignments odd. Okay, it is not 0 or non-zero, but odd versus even. So, odd ones are the number of phi odd, yes instance, number of phi even, no instance. That is the problem, that is the language. And a language L is said to be in parity P complexity class. If there exists an NDTM M such that for all input x is in L if and only if number of accepting paths of M on x is odd. Okay, so parity P is the class of those. It is a weaker version of you could say sharp P, where we are not interested in exact counting, but only the value mod 2, right? So whether it's odd or even. So clearly parity SAT is parity P complete. That is immediate. Under P time reductions. So under polytime reductions, parity SAT is the hardest problem in parity P. This is kind of the definition of parity P itself, like you saw with sharp P. And what is open is it a really difficult question or is it easy? That's not very clear. So is parity P not equal to P? And what is also not clear is it related to NP not equal to P question? So if we show parity P is equal to P, then does it mean NP is equal to P? Or if we show parity P is not P, does it mean NP is not P? Right, because this is only mod 2 counting. From mod 2 deducing exact 0 or non-zero, that we don't know. It's not very clear from the definition, just from the definition. So let us continue exploring this. We will actually give evidence that parity SAT is harder than SAT. It should be as hard as sharp SAT, in fact. We will come close to solving it. So what we will show is, by showing that NP randomly reduces to parity P. Okay, so then it means that parity P is hard. If NP is believed to be hard, then parity P is also hard. So if NP is not equal to P, then parity P is also not equal to P, although we don't get a full proof because this is under randomized polynomial time reductions. And that is where an interesting new idea you will see. So this is the lemma. We will prove now. So Valient-Vazirani theorem, it's called. So there exists a polytime Turing machine A such that if phi is satisfiable, then this Turing machine A will modify phi to get odd number of satisfying assignments. So the probability that A with using the random bits, it will modify phi to an odd, to parity sat instance with high probability. And if phi is not in sat, then this probability is 0. Okay, so let's read this again. So we will transform phi using random bits to another formula, Boolean formula, let's say psi or A. Psi is A of r comma phi, deterministic polynomial time, except that it is using these random bits r now and not too many, right? Because you have to do it in poly time. So r is only can be bigger than the input phi, but only polynomially by a polynomial amount. So this formula psi will be parity, will be in parity sat, which is equivalent to saying that by definition it is odd number of satisfying assignments with decent probability, and if phi was unsatisfiable, then this will also be, in fact it will be unsatisfiable. So in particular we are just saying that probability of this happening will be 0. So idea here will be to prove something stronger. So transform phi to a formula that has a unique, respectively 0 satisfying assignment if phi is satisfiable. Respectively unsatisfiable. Okay, so not only will we make it odd versus even, we will actually make it 1 versus 0. Okay, so this transformation we will give will be so powerful. It will actually make any number of satisfying assignments to 1 and 0 assignments to 0. So this will be achieved by a very useful trick in computer science that's called hashing into buckets. So use basically hash the 2 raised to k satisfying assignments of phi into that many buckets. Okay, so we will apply hash function and map these 2 raised to k assignments into suitable number of buckets, and so you have to see the details of this to understand how this thing is done, how this thing works. Okay, this is the rough idea. So that's the hashing claim. So the way we will implement the idea is through matrix multiplication. Okay, the hash function will essentially be multiplying by a random matrix. So our satisfying assignments will be multiplied by a matrix, and yeah, some linear constraints will be checked. So for a matrix B, which is, let's say, k cross n, elements are 0 1. It's a binary matrix, but 0 1 we think of it as this elements of finite field of 2 elements, and a vector b consider the linear transformation H with this big B and small b parameters as parameters. So, it will send, so think of satisfying assignment or any assignment that's it's an element, it's a binary vector, think of it in the space F2 to the n. So, we will map it to F2 to the k. So, the number of buckets that we are mapping here is actually 2 raised to k. So, that is an important thing. So, 0 1 to the n is mapped to 2 raised to k bucket. Okay, that is the idea. So, the space, the ambient space shrinks. So, that technically we achieve it by using linear algebra. So, F2 to the n is shrunk to F2 to the k, where the relevant parameter t is coming from how many satisfying assignments there were. Okay, so let's move forward with this implementation. So, the way it's done is x is mapped to bx plus b. Okay, so that is, think of x as a column vector and multiply on the left with this matrix. This is possible because b is k cross n, x is n cross 1, right. So, what you get is a k cross 1 vector, which is also b. So, you can then add. So, this is shrinking the ambient space from 2 raised to n to 2 raised to k, and this function here is called a hash function. Okay, think of h as hash function. If you have seen hash functions before, if you haven't, then this is the definition. Okay, it's just a linear transformation, just a linear map, shrinking the ambient space. This is useful in computer science because if your data is coming from a big ambient space, but you know that the data has small amount of information, then you can try to shrink the big ambient space into small ambient space, preserving the information. Okay, so it saves space, it saves communication, and it may also save time. So, that is why these functions are very important. Your passwords, for example, are also hashed. So, it also could help in secrecy. So, the properties that are that make it useful are that for every element in the big ambient space, element x, the probability that the hashed value of x is 0 as you pick the matrices randomly, matrix big B and vector small b. This probability is 1 by the number of buckets. Okay, so remember that in the image space there are 2 raised to k possible values, and the probability that an x randomly hashed will map to this one element 0 to the k, that is uniformly, the uniform probability, which is 1 over 2 raised to k. So, why is this good? So, in our application it will be good because if we already knew that there were 2 raised to k assignments, then when we use a random hash, then this the number of satisfying assignments which will map to 0, that will be unique. Okay, so, we have come up with a transformation which suddenly makes satisfying assignments 2 raised to k to 1. Okay, so, think of it like this with a decent probability. So, the probability is probability we will calculate, but for that we will need this property 1. Okay, this is for the probability calculation. So, we have to in the end calculate the chance that 2 raised to k assignments maps to the single to this specific element 0 to the k. So, what is the chance that x is unique? That probability will come out to be good. So, this is think of this as falling in a bucket. So, x falling in a bucket, what is the probability of that? Then second property is for different xx prime. So, we will need this for probability estimation. Okay, so these are technical lemmas that we will need. So, now the probability that x and x prime have the same hash value . Zero to the k. Okay, this probability is even smaller. So, this is why the hash function is good, random hash function is good. Probability is again on this parameters of the hash function, and so which means that with good chance x and x prime will be mapped differently. Okay, these satisfying assignments, they go into separate buckets. So, that is the main thing, elements going into distinct buckets. So, they get separated. So, that is the probability, that probability is we will show it to be square of the previous one. So, read this as 2 falling in a bucket. Okay, 2 falling in the same bucket, that probability is lower. And third will be, this is the relevant application we are interested in. So, let S be the set of satisfying assignments, you can think of it like that. With the number of satisfying assignments, let us say it is between 2 raised to k minus 1 and 2 raised to k minus 2. Then the probability that number of x's in S that map to 0 is 1, okay, over random hash functions H. So, you pick a, so the experiment is you pick a random hash function by picking random big B and small b, these are binary matrices, Boolean matrices, and then look at where the satisfying assignments are going, what bucket. So, the number of those x's that go to the 0 bucket, that's only 1, it is unique. Okay, the probability of this is, we will show it is pretty good. So, this is, we will show that this is greater than 1 by 8. Okay, so with a decent probability, you are able to make the satisfying assignment unique. So unique X. That's what we have achieved here. Okay. Yeah, so if you haven't seen hash functions, this may feel very mysterious. So let us go through the proof, how such a thing is, how these properties are shown. It's actually simple probability. So proof of this claim. So the first property, so think of first picking B randomly. So if you have already picked big B in your experiment, then all that remains to be picked is small b, right? And you have to pick it so that bx plus b is 0. So the probability of picking b equal to minus bx, right? That's what bx plus b equal to 0 means. So picking vector b exactly this, what is the chance of it? Well, the number of choices of b is 2 raised to k. So the probability is inverse of that. This is equal to 1 over the size of f2 to the k. That's the domain of small b. So that's 1 over 2 raised to k. Okay, so that proves the first property. Now let's do the second one. So the second one we are interested in. So bx plus b and bx prime plus b, both of them should be 0. So that probability is equal to bx is minus b, which should also be bx prime, right? That's the equivalent condition. And so these are two events, so we can, it's an intersection of two events. So let us use conditional probability. So you will get probability of bx prime being minus b given bx is minus b times the probability that bx is minus b. Okay, and then we'll simplify this.